All right. So, kind of here, week 6 materials. I get everything kind of thrown up in here. Just before I get going, I did want to kind of just mention if we can look at the syllabus, just kind of think about where we're at and where we're going. So that second problem set is due when? Yeah, before we meet in class on Thursday. So, these problem sets, a lot of the times it's going back to like more simple stuff than what we've now talked about. So don't try to overthink or overcomplicate it. Sometimes, especially for that problem set too, it's very basic, simple linear regression. Today, in last class, we already started to introduce the idea of multiple linear regression. So things are getting complicated. We've talked about things like heteroscedasticity, things like that. But those assignments, they're meant to kind of be the order in which we've covered things in class. So like the very last question, I think, on that problem set was related to heteroscedasticity. So in all the previous questions before that, that shouldn't be entering into kind of your thoughts, right? So the assignment's really built kind of the same way we cover material in class. Also, just kind of a look forward. So we've now got kind of 2 of those quizzes in. We'll have 1 more quiz, and I'll assign that after Thursday's class. We're getting close to that midterm. So we've got what? This week of classes, next week where we kind of cover some new material, and then a week where we have a review class that Tuesday before that exam, and then that exam would be that Thursday. So what is that, the 6th, right? So it's not too far in the distant future. So between now and Thursday's class, I'll try to get up a practice exam that kind of looks similar to what the format of the exam will be. Now, if you're thinking already about like study materials, that will be a main one. But anything that I gave you in terms of like practice questions for those quizzes, going back and reviewing those old quiz questions, especially the ones you got wrong, those are all going to be good ways to kind of study for that exam. So I'll get up a practice exam here. Like I said, I should get it up before Thursday's class. If not, for sure, Thursday, I'll get that practice exam up. So you can start to think about what that exam is going to look like. And we'll talk more about that as we get closer to it, right? But just kind of thinking about where we're at and kind of where we're going, okay? You will have 1 more problem set before that exam as well. So I'll get that up. I want to go over some of the questions depending on what we talk about today and Thursday. So I'll post it after class Thursday. But there's a couple of questions I might change a little bit depending on what we do. So that'll kind of be ready to go. You can kind of start working on that. It'll have some material that we haven't quite covered yet. So I don't know. I'm hoping we go through things a little bit quick. I think we'll have some time in class to like even workshop stuff together, and like you could even work on it during class and almost use class as like a what do we do here kind of help session. That's kind of what some of this review is built in for. Also, this new material that we have coming next week may not extend both class periods, might only take us 1 class period to get through. Okay. All right. Other than that, the first problem set has been graded. There's a few of them that had some issues that my TA kind of let me know about, so I still have to take a look at those. So if you have a comment or something and you don't have a grade in yet, I need to review those. I should be able to get those tomorrow. I think the most common issue it looked like, just browsing his comments, I can't reread this stuff, right? Like, so these problem sets, you're going to have some code that gives you some state output most of the time. But some of it can be stuff that you literally can also just do by hand, right? So like on that second problem set, just to kind of, maybe I didn't do this, but I can kind of walk through. Oh, actually, let's just pull it up here. In fact, this is going to be kind of similar to what we start seeing on the exam questions. Let me get that practice exam out. On number 6 here, to fill in all these missing blanks, there's literally, you don't need any code, right? I've given you the state of output. In fact, I've given you the code that gives you that output. Here, it's going to be kind of filling in the blanks based off of different things we've talked about. So on problem 6, this is really going to be stuff that you do by hand, right? Now, because you're doing it by hand, if you simply upload a do file that has code, it's not going to have any answers to this question. So what do you need to make sure you do? Either include a Word document, or what did I say probably is preferred? Use comments in your do file, make sure those are in there as well, right? So you're going to need to answer these questions. A lot of the times, if I ask you for what the coefficient estimate is on something, you can't just give me the regress command. That doesn't tell me that you know where to find the coefficient. Now, obviously, that one's a little bit easy because it's kind of labeled. You could probably find it pretty easy. But as we kind of progress, right, I don't know that you're finding the correct statistic using that state of output from your code. Okay, so you need to include your code, but also identify what the answer is if I'm asking you for something. Okay, so if I'm asking you for the intercept coefficient, you can't just tell me reg IQ birth order. It's 105.66, right? Or if I ask you for statistical significance, that means you need to take that p-value and compare it to what? How do we make rejection decisions? If p-value is less than alpha, right? You need to actually tell me what that rejection decision is, okay? So make sure you're doing that. Your do file should have several lines of comments in there to identify what the answer is to different problems. Or if, like I said, you can also include a Word document as well where you kind of do that if that's easier for you. So kind of up to you. Okay. Is that any questions on that before we dive into material here today? Yeah.
It's about this question, but I don't know how much you're allowed to say. It's about the A alphabet that we're supposed to find. I was just kind of struggling, like, is that like on the slides? Do you have an example of us doing that?
Yeah, so anything I ask you to do here, there's likely something that we did in class in the do file that probably kind of lines up with it. I'll give you a little bit of hint on this one. If I want to know the mean of this variable, probably gave you all of this output for a reason. So when we're doing simple linear regression, and we'll use this today with multiple linear regression, just more variables, what are we trying to do? We're trying to come up with a predicted y value for something, given different values for x. Now, when we run this regression, it's going to give us our predicted values for that coefficient. One thing we said is going to be true, we can think about what's the expected value, say, of this slope coefficient. If we don't have any bias, it should be whatever that true effect is. And you can kind of think about is, let's say there's some relationship that exists between wages and the years of education. That's not going to be true for everyone, right? Just because your years of education goes up by 1 doesn't mean your wage is going to go up by $10,000. Some people might go up by 8, some people might go up by, down by 2, right? What are we really picking up with that relationship? It's the average effect of a 1-unit increase. So we said one way we can think about this as well, once we have those coefficient estimates, the average y value will be essentially what that predicted y value would be if we use the mean of x. So if I know these, and I know the mean of y, I can back out the mean of x. Or if I know these, I know the mean of my x variable, I can back out the mean of y. Might be helpful. Yeah. Okay? Any other questions related to just kind of the logistics of these problem sets as before we jump into material here? Okay? All right. So, let me pull something up before I forget. Okay. No, whatever. There we go. So we'll start with the week 6 slides here. And this should all be kind of review, setting us up. This thing gets out of my way. Okay. Get down there. All right. So we talked about multiple linear regression last week, where you start to not just have one independent x or right-hand side variable, but we can try to predict y using multiple variables, in which that sounds a lot more realistic, right? Y is likely going to be a function or a factor of many things. Okay? So we said as we add in more variables on the right-hand side, what should happen to our predictions? If you're using more variables, more information, do you think your predictions are going to be better or worse? Better, right? What tells you if your predictions are better? Or R squared, right? That's one thing we can kind of look at. So when we start to include all of these variables on the right-hand side, each one, right, the total, using them all together, our R squared tells us how predictive all of them are, right? It's like simultaneously, right? How much all of them explain why. However, if I'm throwing like 100 variables on that right-hand side, what's going to be true probably about some of them? If I'm trying to predict something, I mean, even your performance in this class, I don't think I could come up with 100 different variables to that would be good predictors. So if I somehow find 100 variables, like, I don't know, maybe your shoe size is one of them. What's going to be true about some of those coefficients? They might show up as a value, but they're probably going to be statistically insignificant, right? Or we can still make rejection decisions for each individual variable, right? So just because I throw 100 in there on the right-hand side, maybe only 50 of them actually are statistically significant. Those are really the only 50 I should be using. The other 50 are just noise, right? They're just random kind of data I'm throwing in there that don't really explain or help me make better predictions about why, okay? So we can do hypothesis testing for every single variable's coefficient when we have multiple variables on the right-hand side there. Okay? You know, just to kind of go back through, we talked about these with linear regression. We've got some assumptions floating around behind the scenes. I don't stress these too much to ask you if they're violated or not. We will focus on one today, an egregious way that it's violated, but we kind of had here that the expected value of our error given different values for x, or these variables we've included, is 0. This basically just says we don't have an omitted variable bias, right? That the errors that we're making aren't related to anything outside of our regression, right? We don't have this bias built into our coefficient estimates. We also are assuming the data is essentially random. This just means that when we were sampling, you know, a way that this would be violated, some people, researchers get lazy. They find somebody, and what do? They ask them if they have family members. Well, what do you think is true about your attributes with your family members? They're likely correlated, right? You're in the same family. There's likely a lot. So that would kind of break this. You know, that's where we see that kind of getting broke. We don't have large outliers. So this is like, especially with small data sets. I always use the example of, you know, Elon Musk or Bill Gates. You're going to throw our wage estimates way off, right? Or our earnings estimates. And then the one that we're going to focus on today is this idea of no multi-collinearity. So we didn't really have this assumption when we only had one variable on the right-hand side. Technically, we kind of did. We didn't focus on it because we'll see once we talk more about it here in a second, why it doesn't really show up until we get to multiple linear regression. So if all these are met, we say that the estimates are blue, or the best linear unbiased estimate, right? So I kind of said, you know, once we run this multiple linear regression, we can test the statistical significance of each one of these coefficients. Now I have, what are the distributions for each one of these coefficients? I kind of already alluded to this a little bit. And we had that question earlier, but if I'm trying to predict something, and let's say I'm using 3 variables, it could be 4, 5, 6, however many I want to include in the right-hand side there. The expected value of every coefficient estimate should be whatever that true effect actually is. If we don't have any omitted variable bias, that should be the case. Now, what did we say was simple linear regression? If I'm looking at the coefficient estimate, and this could be for any one of my variables, so I'll kind of just call that I. Could be beta 1, beta 2, whatever variable I'm looking at there on the right-hand side. Not only will the mean of those estimates be kind of whatever the true effect actually is, right? They're also going to be, let's see if I can draw this good. There we go. Normally distributed. Okay. So everything we talked about with simple linear regression is going to apply to these coefficients from a multiple linear regression, right? Our coefficient estimate should be normally distributed. So we can do things like what? If I have a coefficient estimate, what could I build around it? So I can turn it into a test statistic and do my hypothesis testing, or we could build a confidence interval. Once again, we technically are going to be using these student t distributions that give us kind of half of alpha on each side, because every hypothesis test we do for these coefficients, we're assuming the coefficient is equal to 0. So we have a two-tailed test. Now, in practice, we can kind of use our z-values to approximate, especially with these larger data sets. And then here, usually like with the mean, this was like the standard deviation of our variable. What I said here, if we're looking at the coefficient estimate, what's the standard deviation of our coefficient estimate? This isn't technically what you're supposed to say, but that's an easy way to remember it. The standard deviation of this statistic or coefficient estimate, we call the standard error, right? And that's kind of in one of those columns, right? For every coefficient estimate we have, we'll look at some data output here in a second. Each one has a standard error associated with it. It's essentially like the standard deviation of that estimate. Like I said, don't tell a true statistician that, but it's easier to think about that way. Okay. Excuse me. So we can do things like build confidence intervals, do hypothesis testing for every single coefficient. for every variable we include in the right-hand side there. Okay. Any questions here? There should be, I guess, a kind of review and rehashing what we've talked about with just simple linear regression. So I've got an example here in a second, but I'll make the point what's going on here. The example in the slides I know is easier, so let's do that one first, and then I'll make something a little bit more realistic. Okay? So this fourth assumption I said was this perfect multicollinearity. So what multicollinearity it means is that you have two variables that are exactly the same value, right? At least for now, that's how I'll reference it. So if you had two variables that for every observation, they're the exact same value, that would be perfect multicollinearity. So I'll show you a very dumb example of this. Let's say I was trying to predict whether or not someone was issued a ticket at a traffic stop. So that's a data set we'll use later on today. And I want to try to use that with a dummy variable. Indicator was the driver male. If I accidentally include the same variable as an independent variable twice, what's going to be true? Every time the driver male variable is a 1, what's true about the driver male variable? It's a 1. What happens every single time the driver male variable is a 0? The driver male variable is a 0. It's the same variable. So that would be perfect multicollinearity. I can make that mistake by doing dumb things like including the same variable twice. Talk about it a little more realistic, what can have perfect multicollinearity even if it's not quite the same variable. Now, good news is Stata recognizes we're being an idiot and it will drop that variable that has perfect multicollinearity. It's like you can't run this regression, right? And that's because when we're looking at the relationship between X and Y, that's what that coefficient is telling us. When we have multiple variables, we're also kind of saying, this is telling us the expected value of whatever coefficient estimate we're looking at, holding constant all the other variables that we've included in our regression. Well, if I hold driver male constant, is there any variation in driver male? No, right? They're the exact same value. So we just can't run that regression. Okay. Now, Stata will be nice and drop for us and let us know you use the same variable twice. That's nice, right? But what if I had something like, hold on. Let's say I have two variables and they are technically different. One of them is the number of years you have been of legal drinking age, right? So once you're 21 in Indiana, right? Starts to be, at 22, it'd be 1 year. 23, it'd be 2 years. 20, so on and so forth. Well, what's that relationship? If I think about these data points, anytime somebody is, say, 21, what's going to be the value? So this is my X and Y variable. How many years have they been of legal drinking age at 21? 0, right? So 21 and 0. Every observation, even if I had a million observations, right? Every combination of this X and Y will always be 21 and 0. Well, what about if they have been legal drinking age for 1 year? Every single person in the data set would be how old? 22. And then 2 years, 23. Every data point is going to fall on this line of prediction, right? Or line of best fit. There's no variation in between this X and Y variable, right? Because this variable is a direct function of the other, right? They are perfectly multicollinear. That's a little bit more of a tricky example, right? Because it's not just like I included the same variable twice. It's a different variable. It is different values, but those values are a direct linear function of the other variable. So a lot of times you'll see this when it does come to things like years, like age, years of experience, right? I can't have 5 years of experience if I'm only, 12. I can't have 5 years of experience on a job. And so a lot of the times it'll be something that's a direct linear function of something else. So we won't focus as much on perfect multicollinearity. We'll talk about it a little bit today. We'll then progress eventually. And once we understand this, we got to walk before we can run imperfect multicollinearity, right? And that one shows up a lot more often. But to kind of introduce this idea of multicollinear, it's when one variable is a direct linear function of the other. Okay? Now, including the same variable twice is a very obvious example. Here would be another one. Okay? There's no variation in the data. Okay? Does this make sense what I'm getting at here? Any questions on this? Yeah.
So, I know a direct linear function, that can describe a multi-term perfect relationship. But does that also apply to like other functions? So like quadratic function?
Yeah, technically, we're only doing linear regression up to this point. The same principles would apply once we get to talking about nonlinearities and you like estimate quadratics. If there is only one function that gives you the y values from different values of x, it would break this. Now, like I said, we're using everything linear up to this point, so we don't have to worry about that yet. But if I told you how many years someone's been of legal drinking age, you can automatically tell me what the corresponding age has to be. Same thing would be even if we had, I don't know, I'm not a biologist, but something like age and telomere length. I don't know, something that's the same across everyone that decreases as we get older. I don't know exactly enough to probably even be mentioning the word telomere. But, right, maybe it could be a nonlinear relationship there that's also just a direct function. Is that what you're kind of getting at? Any other questions on this before we keep moving here? Okay, so probably spent plenty of time on this. Let's see if there's anything else I want to say here. Multiple dummy variables. We'll kind of start talking about this before we transition over. So we've got multiple linear regression, and we'll revisit some of the stuff we talked about last class once we jump over to Stata here in a second. But before we do, I want to set us up for something else. So we also have these dummy variables that are just 1, 0. We can also have like categorical variables, which we can create multiple variables that are all dummy variables, but they're all really kind of collecting information on the same thing. So notice here, like I can include several dummy variables. Excuse me. If it is categorical, this would be something like, maybe I want to estimate what your performance in this class is going to be. And I include indicators for a 1, 0 if you're a senior, 1, 0 if you're a junior, 1, 0 if you're a sophomore, 1, 0 if you're a freshman. Those are the 4 possibilities, right? If I were to include all of those on the right-hand side, what's going to be the issue? Anytime junior, senior, and sophomore are 0, what does freshman have to be? 1. Anytime freshman, sophomore, junior is 0, what does senior have to be? So what issue do I have? If I know the first 3 variables values, I automatically know what the 4th variable has to be. So I've got multicollinearity, right? That 4th variable is a direct function. Now, not of only one variable, but a direct function of the other 3. So anytime I want to have this like categorical variable, like what year are you in class, and I want to create different dummy variables using it, when I run my regression, well, what would the effect, let's say I had that senior variable, how would I interpret its coefficient? It would be the effect of going from the 0 to the 1 group. So being a senior, it would be the effect that that has on the predicted exam performance, but relative to what? What's the 0 group? Well, if I include freshman, sophomore, junior, and senior, there is no comparison. So I have to leave one group out, right? I need to have some comparison group for those other 3. So in my example, what would I probably do? I would probably leave out freshman, right? And now the coefficient on sophomore, junior, and senior, they would tell me the additional expected change in exam performance or test performance of being a sophomore relative to what group is the 0? Did I leave out? Freshman. And we'll run through some more examples here, but I have to leave one of them out, okay? So here I've got kind of an example, just slightly different. So if I was thinking about something like this, what do I have? Years of schooling, and I'm trying to predict wages. And maybe I don't want to do like the number of years of school, but I want to kind of put it into like attainment. So do you only have a high school degree? Do you have, some college, but not a college degree? Do you have a college undergraduate degree? Do you have a graduate degree, right? So these are kind of the 4 different combinations that I have. If I wanted to kind of include all of these, a dummy variable for each one, which one probably makes the most sense to leave out here? So remember, my coefficients on each one of these dummy variables for these different kind of education categories are going to be relative to whatever group I leave out. So if I want to know the predicted wage kind of change from having some college degree or graduate degree, if I leave out high school degree, what would I expect all those coefficients to be? Not zero, right? The coefficient estimates, the slope estimates are going to tell me the effect of being in one of these groups relative to the group I leave out. So what do you think is true about the expected change in wages if I have some college relative to if I only had a high school degree? Do you think wages are going to be predicted to be higher or lower? On average, a little bit higher. What about the predicted change in wages if I'm in the one group for, do I have a college degree versus what group did I leave out? Only having a high school degree. What do you think that coefficient estimate is going to be? Positive, right? So it probably makes sense to leave out either what you expect ahead of time to be the lowest group for your Y variable, or what if I had left out having a graduate degree? What, and I included high school, some college, or college degree. Now all my coefficients are likely going to be relative to what I left out. So relative to having a graduate degree, the predicted change in wages from being in one of these three groups would be negative, right? A negative coefficient or low. So we kind of have to use our best judgment of which one we leave out. Now I'll show you in practice. We can run this, and even if we don't know ahead of time, we can kind of rerun some regressions and figure it out. So we'll look at this athletic revenue data. So let's go here. I've got the week 6 kind of do file pulled open. That should be right there on the main page. It's also under the files tab under week 6, but here we've got it, right? So let's see. I think it's here. Let's see, did I put it there? Yeah, there we go. Okay. So that NCAA revenue data is the one that I'm going to be kind of starting out with. Okay. So once again, you don't have to use the file path. You can download that DTA file and just file open it. But once we have it open, I'm going to run this command. There are some weird observations where they didn't belong to a conference. So I'm just going to get rid of those. Don't worry too much about this. This is just going to keep only the observations that aren't missing that conference variable. So we're all kind of starting with the same one. So I don't know if I've used this command yet, but a nice quick way, and this isn't really practical when you have a nice continuous variable, because the tab command will tell you how many observations are equal to every possible value for that variable. So if I had like wages, what's going to be true if I hit tab on wages? It's going to be like every cent possible income and number. Okay, it's going to be a really long list. But here, this should tell me the kind of number of observations I have that belong to each one of these conferences. So this is across a couple different time periods. So I think this was basketball revenue data. I could be wrong that I had it. But notice there's like the Sun Belt, whereas the Big Ten is right there. We've got all these different conferences and different schools that belong to them. So kind of looking here, I've got different schools, different time periods, the conference they belong to. I've got revenue data, donor data, right? It's a bunch of ticket sales. So I'm going to think about, all right, how can I take this variable that tells me the conference? Because it's text right now. Can I use that in a regression? No, I have to have numerical data, right? Quantitative data. So I can turn this variable into quantitative data by creating dummy variables. One that is equal to a 1 if it's from the Sun Belt Conference, 0 if not. Another variable that's equal to 1 if it's from the Mid-American Conference, 0 if not. Another variable equal to a 1 if it's from Conference USA, et cetera, et cetera. So the way that we could do that is I would have to type this out kind of here. I'm going to create a new variable, which is just a dummy variable. So this was using that gen command. We've already talked about creating these indicator variables if a certain conditional statement is true. So create this AAC, which kind of standing for American Athletic Conference, which is equal to a 1 if that conference variable is equal to the word or words, the text, American Athletic Conference, 0 if not. So notice if I run this line of code, every time I have, well, we have to actually find one. Let's see, this is probably sorted. Oh, there we go. So anytime I've got an American Athletic Conference observation, that variable is a 1. Every time that it's not, it's equal to a, oh, where was it at? There we go, 0. Okay. So the only problem is I could go through and do this for every single conference. That's going to be a lot of typing. Okay. Now, I wouldn't expect you to do the next thing I'm going to show you. This is one of those I'm showing you the power of state if we were to kind of continue past this class. So I could do this all by hand. And on a problem set, maybe I ask you to do something like this, but you would only have to create like 3 or 4 different ones, right? I'm not going to ask you to do like, I don't know, 12 or however many conferences there are. So I'm going to real quick go back to here. And I'm going to drop that variable I just created. Just get rid of it for now. So this line of code here, what you can start to do, if any of you have done any coding, you've heard of loops, right? You can basically run the same line of code, but loop through different values. So here, I want to, for each of these possible conference titles, go through my kind of, go through all the data. And if that conference abbreviation variable is equal to AAC, I want to put a 1 there. If it is, 0 if not. I then want to go back through, create another variable, which is the Big Ten. It's going to be equal to 1 if that conference abbreviation is equal to Big Ten, 0 if not. Then it's going to go through, create another variable called Big 12. It's going to be a 1 if the observation is equal to Big 12, 0 if not. I'm basically going to run through all these possible values that I could see. And let's see, where's the abbreviation? For that conference abbreviation, and create a bunch of different dummy variables that are kind of identify what conference it belonged to, right? So if I go ahead and run this line of code, you'll notice every time I have an observation where it's AAC, the AAC variable is a 1, 0 if not. Every time I have that conference abbreviation variable, Big Ten, it's a 1 if it is, 0 if not, so on and so forth. But it was a way where I didn't have to like type out every single, I can run kind of this loop and it very quickly creates a bunch of variables for me. Okay? And once again, I won't expect you to do that. But if I did ask you to do something like this, you could also create 3 or 4 by hand, right? I don't think that would be, shouldn't be terribly time consuming to do that. Okay. Any questions? I'm doing a bit of a hand, kind of glossing a little bit there. I'm not gonna expect you to do loops, but you can do them to make life a lot easier, right? So I'm now going to finally get to my regression, which is very naive, but I just want to predict total revenues from what conference this school belonged to, right? So I don't know how much we know about college athletics, but which one of these conferences, if you had to guess, would you expect might have the highest predicted total revenues? If you've ever been to an SEC football game, it's absolutely absurd, right? Like the amount of the culture in the South is college football is huge. I would expect SEC might be the largest. Big Ten's probably pretty large as well. What might I expect pretty low coefficients on? I don't know, maybe the MAC, schools like Ball State, things like that, right? So I'm going to try to run this regression. And I'm going to include a dummy variable for every single possible conference I had here. What's going to be the problem with that? If I try to do that, it correctly identified for me, you had some multicollinearity, right? You had to have a comparison group. You had to leave out one conference. Now, the one it chose for me, and I think the way it does this is always the category that has the lowest number of observations. So it left out independent, right? I think that's the default. So notice here, compared to this independent school, which, how much do we know, but this is a little bit older data. What school do you think this probably was? They make a ton of money. Notre Dame, right? So relative to really just one school, Notre Dame, how much, if a school belonged to the Big Ten, how much more would you expect their total revenue is? Well, quite a bit, right? So here, when we used to be dealing with like e to the negatives or negative, that means move the decimal that many places to the left. Positive 0.7 means move the decimal 7 places to the right? So the predicted increase in our Y variable of total revenue, if the school belongs to the Big Ten versus if they're independent, you would predict that their average revenues go up by what? 70 million? No. Yeah, 78 million if I'm looking at that, right? So pretty large expected increase there. Okay. So if I was Notre Dame, what might I think of doing? Joining a conference, right? Now, which one of these conferences would I want to have joined? One that had a positive coefficient, right? Because that would mean I'm better off. If I had chose one with a negative coefficient, that actually means my expected revenues would be lower than if I remained independent. So instead, I'm going to run a slightly different regression. If I'm looking at these coefficient estimates, instead of allowing Stata to choose, so if I tried to run it with every conference, it kicked one of them out automatically. It identifies the perfect multicollinearity. If I was going to choose to run this regression and leave one out, which one would you choose? So you look at these coefficients, some are positive, some are negative. If I want them all to be positive, which school would I leave out here? Or sorry, which conference? So which one of these conferences is going to have the lowest predicted total revenue? The one that has the... So if I'm making predictions for Y using all of my X variables, right? What's the only time these coefficients will get added into my prediction? If the school belongs to that conference. So if I'm adding in a positive value, that means that conference has a higher predicted total revenue. If it's negative, lower. So what might be a good base comparison? The conference that has the highest coefficient or lowest coefficient. If I leave the one out that has the highest coefficient, which is what? The SEC here, what's going to be true about all my coefficients? Well, remember, they're indicator dummy variables. So it's belonging to the one group relative to the zero, which is the group I left out. So if I leave out the SEC, all of my coefficients will be the expected change in my Y variable of total revenue from being in this conference relative to the conference that's earning the most. So I know my coefficients would all be negative. If I leave out the conference that is earning the lowest amount, now all my coefficients should be positive, right? So we can kind of prove this to ourselves. So here I've got one. I'm going to leave out, I think I left out the Sun Belt. So that was the lowest conference. Sure enough, all of my coefficients are now positive. And it's going to be the same kind of predicted differences between all these. It's just going to make the coefficients a little bit easier to look at, right? What if I left out SEC? Oh. So let's say I did this one instead. Copy, oh, didn't want to delete it. And let's say instead of the Sun Belt, I include Sun Belt, but I leave out SEC. Now when I run this regression, sure enough, all these coefficients will become negative. With it's not my constant, well, that's not true, right? It's only these dummy variables I'm talking about, their coefficients. Okay. Any questions on this before we keep moving? So using these, because it's going to be a little bit easier. Let me see if I had something in the code. I don't think I did. What would be the predicted difference? So it's very easy here for me to ask you, what's the predicted change or difference in the total revenue between, let's say, the Big Ten and, I already forgot which one we left out, Sun Belt, right? You just look at the coefficient. But what if I ask you, what's the difference between the expected total revenues for the SEC and the Big Ten? How would you find that? So if you have these coefficients, right, we'll start to think about what we're doing, right? So we've got total revenue. Got SEC. We've got all these other conferences. Oops, that would be helpful. Okay, so this is essentially our regression equation. We've got every conference, we left out the Sun Belt, right? So each one of these coefficient estimates that we see is the predicted change from being a 1 for this variable relative to the group we left out, or the 0 for this variable. So that tells me the predicted change in total revenue for being part of the Big Ten relative to the Sun Belt Conference. And if you don't like sports or this example, this could be states and predicted revenues, right, from any business, right? So what's the predicted difference between the total revenue of a SEC school and a Big Ten school? What would I do to find that difference? Well, if I'm making a prediction for the total revenue for a Big Ten school, what's it going to be? The estimate for the intercept. Okay, this becomes a 1, so plus beta 1 hat times 1. Well, if I belong to the Big Ten, what's true about every other conference? 0, so just a bunch of zeros there, right? So I'd have what? Beta 0 plus beta 1. So this is for the Big Ten. What if I wanted to predict total revenue for an SEC school? I'd have my intercept. Now, this, do I belong to the Big Ten? No, so that would be a 0. Now SEC is a 1, so I would get added in the coefficient on the SEC conference plus all zeros. So what's the difference in the predicted total revenue of an SEC school compared to a Big Ten school? Just be the difference between their predicted revenues. What happens to the intercept in that case? Cancels, and I'm left with simply the difference in the coefficients on those two conferences or on those two groups, whatever two groups I'm trying to find the difference between. So I don't have to rerun this regression every single time if I want to make comparisons between different conferences and then say leave out the SEC group to make that comparison. And if I want to compare the MAC, I have to leave that one out. I can use the coefficient estimates, to compare the predicted total revenues from any of these combinations of the conferences. Or like I said, you could do states, and then the revenues expected from different companies or different departments in every state. Any questions on this idea before you? Yeah.
So you're taking the difference, coefficients.
Mhm.
You take it straight from the regression, or do you have to plug it back in?
Nope, that's like the beauty of it. Excuse me. We don't have to rerun this regression every single time I want to compare to a different conference. How much more does the SEC make than the Big Ten? I don't know. Looks like it's roughly what? 10 million, 15 million, if I'm looking at the numbers correct there. Basically, right, 1.12, so it'd be what? Move it 8 decimals. So 112 million minus 96.3 million, whatever that ends up being. If I instead wanted to know, well, how much is the predicted total revenue of the SEC different from the Mountain West? Well, then what would I do? Just take the coefficient on the SEC and subtract the coefficient on the Mountain West. So I don't have to rerun this regression every single time. I can use the coefficients just from my single regression. Yep. Is that what you were asking? Any other questions before we keep? Okay. Let me think. I think there's 2 more things I want to show you here. And then see if I've got an example. Yeah, we'll save that for next class. So just to kind of show you other ways of doing this. So I showed you the way you can do like this loop and then include every single one of these variables that I created. There's a much easier way of doing it that I would highly suggest, right? Now, it doesn't allow you to like as nicely leave out a group that you want. So the way that we just did it is kind of what you have to do if you want to choose what group gets left out. Notice if I run this command, this regression command, and I've got this conference abbreviation variable, which was the one that we were using to create all these dummy variables, right? It was like AAC, Big 12, PAC, right? It's not numerical, right? I can actually use a non-numerical variable in my regression command. If I put I dot in front of it, what that will do is for every unique response for that variable, it will create a dummy variable and include all of them in our regression, which is essentially what we just did. So if I use this IDOT command, and go ahead and run this. Whoops, why didn't it like this? Oh, because this is text, right? All right, well, I forgot. The IDOT command can be useful, but I still need a numerical variable in order to use it, right? So what you can do is use the encode command and create a new variable, which is going to take that old text variable, and for every unique line of text, it's just going to assign it a number, right? So like AAC would become 1, Big 10 would become 2, SEC would be 3, Sunbelt would be 4, etc. So you're going to first put what variable do you want to encode? It's going to be the variable that's text. That, I can't use text with this IDOT command. I need to change this to numbers. So I'm going to encode that original variable, generate a new variable, which I'll be able to use in my regression that replaces that line of text with a number. So if I run this encode command, notice for every conference abbreviation, it looks like it created a variable, that conference reg variable. It looks the exact same. Although what's different between those two columns? Unless you're colorblind, right? One of them's blue and one of them's red, right? So anytime you've got blue, this is going to be that it will display to you text. But if I click on these observations, notice the Big 10 is actually a 2 stored in the data. And the MAC is actually the number 6. So it still keeps that text, but it assigns it a number so that you can use it in your regression. So now when I go back to this do file, now when I try to use the IDOT command, right? Hopefully I don't get an error. Nope. It created an indicator for every single one of those conferences, right? Every possible value that I could have for that variable, and it included them in my regression. Now, once again, the only problem is I can't choose which group I leave out. And here, I can't even remember the default that IDOT uses because it's not the lowest number of observations. Notice here, it didn't kick out independent. It looks like it kicked out what? Actually, I think it kicked out the AAC, didn't it? The American Athletic, yeah. So it'll choose one of them to kick out, right? I think this might be, yeah, it is the AAC. So I think it just kicks out whatever the one group is. I think that's the default. And I believe there is a way you can play around with some settings and choose, but it becomes pretty convoluted. So this is helpful, right? This is useful because I don't have to create all these variables myself, but it kind of defaults and it gets to choose what group it's going to treat as that 0 or that comparison group. Now, that ultimately doesn't matter because we said, what if I want to know the difference between any of these two groups? What do? Just take the difference in their coefficients, right? So it makes it a little bit harder for me to identify, okay, what group was left out, especially if I've got, maybe if I had like 30 different, now I have to like, okay, which one did it leave out? But it's just another way of doing it, okay? Any questions over anything there before we kind of keep moving? So if I asked to do this like on a problem set, I would probably use the IDOT command instead of creating every single variable myself, just a lot quicker. And you're going to have all the information that you would need to answer any questions. It's the same coefficients, right? It's just that the comparison group is changed. Yeah.
How can you tell which variant?
So I can't from what it tells me here. Like I said, I believe it defaults to whatever is the 1, but in order to even figure out what that is, I have to go to the data and actually look at, okay, which of these conferences don't show up in my regression? Like there's no easy way. I have to actually go back and look at the data. Oh, sure enough, it's the AAC doesn't show up. And that's about a value in my data set. And it'll only ever kick out one of them. So it's not like you have to hunt through the data, right? It's as soon as you find, oh, that conference wasn't in that IDOT regression, that's the one that it left out. Yep. Any other questions on that before we keep moving here? So I've got more examples, which we'll kind of use in next class. So we didn't get super far into this today. We'll do traffic style. Let me see if there's anything else I wanted to say. We'll do all this. I can save this because I'm getting some confused looks. So I want to make sure we got some time to review stuff. So going to release this instead of going through it with you. Okay. Well, hold on. Why does it say 3? Let me double check to make sure it's going to be displaying to you right. It should have 1, 2, 3. Yeah, okay. We got 4 questions there. I just have to change the points. So there's that in-class quiz 5, which you should be able to find on kind of the main page. So I'll work through this with you, right? But I put time into these for a reason. What do you think as I'm talking about getting closer to the exam? What might these in-class quiz questions, even though we worked through them a lot together, what might they be good to do? Review them, make sure you know how to get the right answer right, studying for the exam. So we kind of started up. We've got what, another 25 minutes, so we'll easily get through this and we'll probably start kind of some new material. But I wanted to also rehash or kind of revisit some things we talked about last class. So we'll skip questions 1 and 2 for now. Oh. There it goes. Okay. Try not to touch anything too hard. All right, sorry. So we'll go through questions 3 and 4 first, and then we'll go back and revisit 1 and 2. Okay. So you should be able to open this up. You guys seeing it on Canvas or no? So if you go to the main homepage and you click on in-class quiz 5, is it showing up? No? Oh, well, that'll do it. Huh? Thank you. Now you should be able to open it up okay. Sometimes when I scroll, I accidentally scroll through the AM PM. All right, now can we get the class quiz popped up? All right, there we go. Is it working for everybody now? If not, stop me here. It's not? Nope. So go back to the home page and like refresh and try to reopen it. So if you go here, it might take a second for it to kind of refresh that due date. Now is it going? Yeah. Everybody, anyone still having problems with it? I'm sorry for that. It's been a little sleep deprived at times. So I didn't notice the AM. All right. So question 3. If I'm running a regression and I had this data and it was like NFL data, but it doesn't really matter. Once again, this could be positions at a firm and the total value of that worker's contract. So I've got the total value of these different NFL players' contracts, and then I use this IDOT command. So position is going to be the position that they played on the field, right? So quarterback, kicker, wide receiver, if you're not super familiar with football, there's all these different positions, okay? What is this IDOT command going to do? It's going to include a bunch of what? On my right-hand side. So it creates 1-0 variables, which are dummy or indicator variables. Right? That's what we just did. So hopefully this looks familiar if we're paying attention, right? So notice I now have all these different coefficients associated with all of these different positions that the player could belong to, right? All these different groups. Now, one of them had to be left out, right? That was what we said. We need a comparison group. I'm letting you know that the group it left out was the center position, right? The person that hikes the ball to the quarterback, if you're not familiar, right? So got quite a few observations here, like 2,000. Notice if I'm looking at these, first of all, we didn't really talk about this, but what positions could I say make a statistically significant different amount of earnings or total value of their contract from the center position? So which of these positions can I say with, let's say, 90% statistical or confidence, can I say are statistically significantly different than the center position, which was the group that's left out? So what column do you think I would look at here? My p-value. So every single one of these dummy variables has a p-value associated with it. So at the 90% level, can I say that cornerbacks actually make any more or less than the center position? not even close. That p-value of 0.7 isn't going to be less than any of our alphas, let alone 0.1, right, for the 90% level. So I'm going to go through all of these. In fact, there's no position I can actually say makes a statistically significant more or less amount than that center position until I get to the quarterback, right? In that case, they're making not only can I say that it's different at the 90% level, I can say it's different at the 99.9% level here. The p-value is basically 0. Now, while other positions are close, so this kind of goes to our point. Okay, the tight end and running back and tight end positions, those aren't quite statistically significant, but this kind of goes back to, like, in practice, let's not just toss things out because it doesn't quite meet our threshold. I mean, they're very close, right? They're not quite less than 0.1, but they're pretty close, right? Maybe if I had more data, I could kind of get slightly lower standard errors, increase my test statistics. Maybe I would find they are statistically significant, okay? But here, really the only position I could say is statistically different than the center position in terms of their total value of their contract or their predicted total value would be quarterback position. Okay? Now, that doesn't mean I can't interpret these coefficients, right? So if I'm looking for what positions would I expect on average to make more than that center position, it would be all the positions that have a coefficient that is positive. Yeah. So defensive linemen, offensive linemen, and quarterbacks, right? Maybe not what you initially would expect, but remember, these are average effects, right? So what if I wanted to know the difference between a running back's predicted salary compared to a wide receiver? Well, my comparison group is center, so I can't look at one coefficient here, right? But if I wanted to know the difference between a running back and a wide receiver's predicted total value of their contract or their salary, how could I use these coefficients to do that? Subtract what? The coefficients on those two groups, right? So what? 33 million minus negative 13 million. So roughly, am I looking at this right? No, I'm saying 30. Sorry, 1.3 and 3.3 million. So roughly about a $2 million difference. Right? If I use the actual values here, it looks like it's just over 2 million. Right? So all I was doing there was taking that coefficient on the running back position, coefficient on the wide receiver position. The difference between the two told me the predicted difference between those two groups. Okay. Is that clear? Are there any questions on what I'm doing there? Or maybe writing some of this down since it's not like in a slide or anything. Is that okay? Okay. All right. Let's say instead, I wanted to know the difference between a punter salary or total value of their contract and a kicker, right? So place kicker versus a punter. If I don't want to kind of do what we just did, where we look at the difference between coefficients, and I want one regression, right? What are two possible ways that I could get just one coefficient that tells me the difference between the predicted salary or total value of the contract of a kicker versus a punter? One way I could leave out the kicker position. Then I'd be looking at the coefficient on what? On the punter position. That would tell me what's the predicted increase if the player was a punter relative to the group I left out, which was a kicker. Now, what's another way I could also find that same difference? Instead of leaving out the kicker, I left out the punter. Now, if I leave out the punter, the kicker's coefficient will tell me the predicted difference between being a kicker relative to the group I left out. Now, what should be true? Those won't be the same value. They'll be the same magnitude, but in one of those regressions, the value would be positive, and the other, it would be negative, right? Because one of those positions has to make more, right? So I can always, there's kind of multiple ways of getting at kind of having one coefficient. I have to leave out one of those groups that I'm interested in. Now, I don't have to, right? That was kind of the point of question 3. If I use like the IDOT command, I can always use the coefficients in my regression output to then determine what that difference is. In fact, if we were to run this regression, even without doing so, if I left out punter, what would be the coefficient on kicker? It's a little tricky, right? So from this regression where center position was left out, How could I tell the difference between the total value or the salary of the kicker and the punter? Simply take the difference. So it looks like it's what? 3.3 million versus 2.4. So we're talking about what? Just under a million. So we'll call it a million just for the sake of. Now, if I run this regression and I exclude punter, what would the coefficient on kicker be? So we know the difference is about a million, but who's making more here? So remember, this is what gets added into our predicted total value. So who's making more, the kicker or the punter? The kicker, because that coefficient is a smaller negative value. So if I exclude the punter, the coefficient on kicker would be positive, just under a million. Okay. So these are just thought experiments. I'm not gonna you don't go through this every single time you run these, but it's kind of helping kind of, pull all these concepts behind what we're doing with multiple dummy variables here. Okay. Any questions on this before we keep moving? Is there anything else I want to say here? I don't think so. We're good with this for now? Yeah.
Sorry, could you just, so if we left out the punter,
Mhm.
find out the difference, then that difference should be negative.
So if I leave out the punter, right? When I was making predictions using these coefficient estimates, the punter made about $3.3 million less. The kicker made about $2.4 million less. So who's going to have the higher predicted salary? So the kicker. So if I leave out the punter, now the coefficient on kicker tells me this is the effect of being a kicker relative to the group I left out. So it should be positive. Yep. Any other questions? This before we keep. And sometimes maybe writing out what those predictions are, because these are just 1-0 variables, that the predicted total value of a kicker would be what? The constant plus the kicker coefficient. You can actually figure out what that value is. What's the predicted value of a punter? The constant plus the coefficient on punter. You could then just compare those two. That's another way of thinking about doing it as well. Kind of writing it out sometimes might help you see it. Go through these first two. So this one is touching on something that we talked about last class, but I know that I'm going to ask you questions on the exam since I'm writing it. So let's go through this one. So let's say I actually did this in my B251 class this morning. I didn't really go through all of it with them in detail, but I gave all the data, and they have these tutoring sessions, right? And I can see how many they attended. And I actually ran some regressions to see how that correlated with their exam performance, holding constant other factors. And you can actually find, lo and behold, guess what the sign of this is? Positive. So I don't have to tell you that they're good. I can actually have data that supports that. So if this is the number of sessions, right? Let's say I have a variable, and this is kind of to the point where let's say there was this other important variable, and it's going to be something that it's like a lot of the examples I've given you, it's data that might exist or I could collect with surveys. I can't really measure someone's internal drive, right, towards a course. I just can't. I can have indicators of it, but I can't really measure it, right? So it might look like if I exclude this important variable, when I come up with this coefficient estimate between the number of tutoring sessions attended and exam scores, it looks like it's positive, but we know that if I have an important omitted variable, like what is the internal drive of the student, I'm going to end up with a bias. So this would be covariance of internal drive. I'm running out of room here. And then the variance of number of sessions. And then that gets multiplied by what the effect would have been from that variable if I had included it, right? That was kind of what we called our omitted variable bias. So the problem is if I run this regression, it's always going to be positive. Why? what type of students do you think are attending more of these sessions? Ones that care about their grade, we're putting more time into studying. So what do you think probably is true about students who are putting more time into studying in their exam performance? It's also positive. So I might not be picking up the real effect of these tutoring sessions. I might be picking up the effect of this important omitted variable like the internal drive, right? Because that's going to impact things like how much they study. So if I were to include that variable, what do you think the sign of beta 2 likely would be? Positive, right? If I have an internal drive, I'm doing all the other things, right? Reviewing the materials, doing other things in my free time, that probably lead to higher exam performance. What do you think is probably true about the covariance of students that have a higher internal drive and whether or not they can get their ass to one of these CL sessions on Thursday night or Sunday evening or Sunday afternoon? Probably positive as well, right? The ones that don't have a very strong internal drive aren't going to make the track, especially when it's cold out like this semester, right? So it's likely that I've got a positive covariance between that omitted variable and the variable I'm trying to figure out the effect of. And the effect of the excluded variable is also likely positive. So what would the sign of my bias be here? Well, positive times a positive divided by what is variance? Always positive. I probably have a bias that's positive here. I'm ending up with an estimate that's a little bit too high, right? It's probably that these tutoring sessions, yes, they are helpful, but it's probably picking up a little bit of the internal drive effect from the students as well, okay? So I'm thinking about what's going to be true if I don't include that variable. I probably have a positive bias there, right? So we can start to think about these type of examples and putting a sign to that bias if we have these important omitted variables that we might not be able to collect data on. Okay? Now, what maybe is something I could do as a teacher to try to run a better regression, maybe I give them a survey and ask them how many hours did you study for the exam. That gives me some measure of internal drive. It's not going to be perfect, but it gives me some kind of measure to start to kind of try to eliminate that bias, right? You guys probably don't care about that example, but I think it's interesting. I don't know. I mean, you can do this with anything, right? Like this is unfortunately how I see my everyday life, right? I see data and I see ways I can prove things to people without just saying them. Because anytime someone just tells you something, you're like, yeah, there's definitely data that you should be showing me that either supports that or goes against that. And if you're not showing it to me, what probably is true, probably doesn't, support it, right? So we want to understand all these pitfalls that we can have with like basic statistics, though. We want to make sure we're getting a really good causal relationship. So we want to eliminate that omitted variable bias. Here's another example I thought was kind of interesting. So same kind of setup. So I had the number of sessions they attended here. Which of these 5 variables, I've got it identified here, so it's pretty easy for us here. But I'm thinking about perfect multicollinearity. So another example of maybe how this could exist is sometimes you'll have data where it measures something continuously, but then it also has a dummy variable, right? So on this one, like let's say I had the quiz scores of the students in the data set, the number of classes they attended, a dummy for whether or not they included at least one tutoring session. So it doesn't matter if they went to 4, 5, 1, that would be a 1. They didn't go to any, that's a 0. Right? And then did they attend at least one class? And then what was their IQ? So which of these variables would cause perfect multicollinearity with the number of sessions they attended? Well, anytime number of sessions is 0, what is this attend at least one tutor variable going to be? 0. Anytime that number of sessions attended is 1, what is the attend at least one session going to be? What if they attended 2? It's always going to be a 1. 3 is always going to be a 1. So if you tell me the value of the number of sessions they attended, I automatically am going to come up with the same value for this other dummy variable. They're perfectly multicollinear. What are 2 other variables I have up here that I could not include at the same time in my regression for that exact same reason? The number of classes attended, and did they attend at least one class, right? Because there, if you tell me the number of classes attended is 0, what's the attended at least one class variable always going to be? 0. There's no variation in the data between those 2 variables. Either tell me one's a 0, you always know the other's a 0. If I tell you the other's a 1, you always know the other one's a 1, or a 2, it's always a 1, 3, it's always a 1, etc. Okay. So this can sometimes occur with data sets where like you have like these dummies that kind of identify like, just was this a any value, like something like this can occur. So you have to kind of watch out for that too with perfect multicollinearity. Excuse me. And we have 5 minutes. So first of all, any questions on that idea before I kind of try to close this out here today? Should be able to get that submitted here. Next 5 minutes is when it's due. So we went through all of them. Should be easy points as long as you're attending class. It's also, I think, helpful to kind of go through problems like this. Like I said, these are kinds of questions loosely that you'll see on the exam. At least give us an idea of kind of what the topics and kind of content will look like. So next class, where do we end off? I'm going to start looking at this traffic stop data. So we're going to do some, I think it's kind of cool stuff because we're going to start to identify, it's just traffic stop data, but it's basically sets us up to be able to identify discrimination really in anything. So we'll use dummy variables and kind of push the concepts a little bit more, thinking about how we can do that. Let me think if there's, we did this kind of an additional omitted variable kind of in the in-class quiz, so we might skip that next class. But we'll just keep on going with multiple linear regression. I'll probably start rehashing some of the stuff we've already talked about. We don't have a ton of new material, but I think seeing it kind of in Stata will also be helpful. Other than that, any last minute questions on that problem set? I'll have office hours tomorrow. Feel free to stop by. Try to stay warm, and I'll see you guys on Thursday.